Any questions or observations? Otherwise, we can move on to the coffee break.
So this is something I've always wondered, and I'm hoping you can clarify it for me, and I think you talked about it at the end there. So suppose we do your spin experiment that we were talking about, where we have a particle and we've got a magnet that we can orient, and let's just say we can put it in the x direction, we can put it in the y direction, or we can put it in any combination of those, right? And what I'm trying to make sure I understand is which languages, which descriptions of this situation requires the non-classical probabilities. So one thing I can do is I can describe the underlying quantum state of the particle as with just a vector that is some combination of x and y. And if I don't know the state of the particle, I could have a classical probability distribution over the possible states of the vector. So that's one thing I could do. That's classical. The other thing I can do is I can say, given that I'm going to orient my magnet in the x direction, what are the possible measurement outcomes I will get? And that also, as you just said, is a simple Boolean algebra, and I get classical probabilities. So the place where I get non-classical probabilities is if I insist on talking about, is the electron, what is its spin in the x direction, right? If I say, what's its spin in the x direction, the answer could be up, down, or neither. And then if I say, what does it spin in the y direction, it could be up, down, or neither. And when you put all those sorts of propositions together, you get a non-Boolean algebra, right? So it's at that level of talking where I insist on talking about what is the spin state of the electron, or whatever, of the particle itself, not talking about how are my measurements going to come out. It's when I talk that way that I run into the non-classical logics and the non-classical probability and things like that. Is that right? Because I've always just wondered and wanted to get that pinned down.
If I understood correctly, I think that you are right. And it is important to consider this example, which is not... I think that it is better if you start with this. Take Fermion mechanics. You know Fermion mechanics. The ontology is classical. It's just billiard balls moving in space-time according and interacting with a weird potential, which we don't know what it is, but the ontology is completely classical, and the probabilities lying and governing the behavior of the hidden variables are classical. So that is a concrete example. So do you want classical probabilities? Yes, they are not gone, of course. But be careful, because if you want to solve, I don't know, a concrete quantum problem using Fermion mechanics, it might be very difficult. So it is not a question, a matter of you're obliged to use Non-Kolmogorovian, but it is very useful. This is what I'm pointing out. This mathematical machinery is very useful. The one of using, instead of an abelian algebra, we are using a non-abelian algebra of observables that allows you to represent order effects, because if you measure this and measure that, might be not the same of measuring this and that, or you can do this or that. Sometimes this mathematical machinery makes things simpler, making it to be the right approach to many problems. In that way, of course, if at the end of the day you don't like this non-Kolmogorovian, you can go to sleep and think that, okay, it's okay. You wake up in the night like sweating, dreaming about non-classical logic, quantum probability. Oh, no. There's always Fermion mechanics. But perhaps that makes you feel comfortable with your faith, but it is not so useful. And I'm not saying that Fermion mechanics is not useful. For some concrete problems, it's useful. There's a guy that applies Fermion mechanics to economical problems, modeling markets. I'm not saying it is not useful. What I'm saying is for many applications, it is better to use the non-commutative, at least for quantum mechanics. Of course, we can argue whether it is useful in other disciplines or not. Some people claim that very strongly. I will be cautious.
Yes, if I understood well, random variables in the quantum probability are the same objects that are in the in the classical model, and if not, do you have in the quantum probability something related to the equivalent to law of large numbers and central limit theorem that allows you later on to do test hypothesis, which at the bottom end allow you to make decision, which is the goal that you want for application to make decisions. So do you have all this equivalent machinery in the quantum setting?
Yeah, my answer is yes. You can use, for example, Maxent principle, you can use inference methods to figure out which is the unknown quantum state and so on. And in general, everything must work because when you perform a concrete experiment, it is classical. So the law of large numbers works there. So suppose that you speak about the Heisenberg uncertainty. If you want to test it empirically, what you have to do is first prepare the system in a quantum, prepare a quantum state, then make infinitely many copies of it, and then take a subensemble and measure position, and you will end up with a curve, and you will compute the variance, right? And then you do now a complementary experiment and do the same for momentum. And everything works there, and it has to work, otherwise it will be meaningless. And then you gather everything together and then get the uncertainty relation. But all usual statistical considerations work, provided that you make the mutatis mutandis changes. I don't know if that counts as a question. Yeah. But you have a kind of inference theory in quantum mechanics, so you can, yeah.
That's the way.
And again, in each classical context, you can apply Bayes' theorem, Bayes' rule, and there is quantum Bayes' rule. There's a lot of people working on that. But I might say that this is an ongoing field of research.
Thank you.
Okay.
Thank you. So this, I guess, ties into the last thing you were saying in response to the previous question. I was partly just kind of curious about how updating would work in the quantum case when you don't have standard conditionalization, and also whether, so you say, right, we can always, if we want to, you can always keep the standard Boolean algebra, you just have to have more stuff in there that sometimes you can't see. And whether sometimes it seems like, I don't know enough about quantum mechanics to know this, but it seems like sometimes I might want to update my beliefs based on things that aren't observable, so that I learned that something's in a superposition. I haven't seen the outcome yet. Maybe I learned this in a superposition, I want to revise my beliefs. But those superpositions won't be represented in the algebra. It seems like that's going to be a cost for going to the kind of quantum version of the information, or quantum version, instead of just keeping all the propositions represented. Is that right, or is that not?
Well, let me complete it.
Yeah.
Because superpositions can be represented in the algebra. You can. All possible states and superpositions can be represented. But the problem that I see when you speak about updating information is that information really there? Here it comes to interpretation, because there's a great debate in quantum mechanics about hidden variables. But it turns out that you cannot, they are hidden. So don't try to update because they are hidden. You will never know by construction, which is a very odd epistemological notion. No? It's something that you cannot control and you will never know. It's not just something abstract like a magnetic field. You cannot look at magnetic fields, but you can prepare them in different states and measure. So there is control on this abstract thing. But that is one thing. And then if you stick to a very Copenhagen ontology, there's nothing to update because there's no position of the particle. So it turns out that when you prepare the quantum system and make one measurement, usually you destroy the system. So, for example, if you measure a photon, the photon will be absorbed and he will never be there anymore for you. You will have to prepare an identical copy and do the experiment again. And it will yield a different result and so on. So updating is tricky here because perhaps if you take this radical ontology, there's nothing to update. But from the mathematical point of view, it works because, let me show you an example. I don't know if this will answer your question, but I think it's interesting to know. You know the max end principle. If you don't know nothing about throwing a dice, you will put probability 1/6. But then I come and I tell you, no, someone comes and says, no, Federico is cheating. The first phase appears with probability 40%. And now you gather information and you will update. And that you can do in quantum mechanics. It's just replacing the classical states, which will be a simplex with the more general geometric object. In this object here, you have measures between probabilistic distributions. You can compare them, and you have a function of being close. You have a notion of being successful. You see? So you can update. If I give you not too much information, you won't know much about the unknown quantum state. But if I give you more and more information, you will be able to determine the quantum state. But now the thing is that the object that you want to determine is not a defined thing. In classical probability, if something is classical and you start to update, you will end up. The guy was seated there, or there were 10 persons in the room. Before that, you had a probability reflecting ignorance. But here, you don't have ignorance, because the only thing that there is, according to this orthodox formulation of quantum mechanics, is a probability distribution. And you can update. The probability distribution, you can update. So I think that, I don't know if this is answering your question, because as you can see, it's tricky, because you measure and you destroy or perturb. So what is updating? You have to be careful.
Yeah, I mean, I was wondering, does it look a lot like Does it look a lot like the ways for updating? Does it look a lot like standard conditionalization, or does it look, something more generalized to just kind of more just of a technical question there?
No, I don't know, because the conditional in quantum mechanics is tricky. Because when you want to define the conditional for infinite dimensional models, you have to be very careful with the mathematics, especially for continuous spectrum. For a discrete spectrum, it works quite well. I can give you a book where, but I don't know the end of the story with that, because things that you don't follow, because I don't know. But there's a very concrete sense in which you cannot update information. I will have to look up Jeffrey conditionalization, but so I don't know.
So thank you again, Professor Federico.
Thanks you.